Higher. If anybody has anything. Addie? 25 on section 3.4. Okay. This is the one, right? All right. So when I look at this, I see a chain rule because I see a function inside of a function. I see the outer function is 5 to the x, and the inner function is negative 1 over x. Agreed? So when I do the derivative, I'm going to do the derivative of the outside. So do you remember the derivative rule for things of the form a to the x? Okay, it's a to the x times the natural log of a. So if it's e to the x, it's e to the x times the natural log of e, and the natural log of e is just 1, so the derivative of e to the x is e to the x. Thank you. Okay, no problem. So I'm going to have 5 to the inside function times the natural log of 5, and then times the derivative of the inside function. Okay, there. That's my chain rule. So now I still need to do this derivative. I'm going to think about negative 1 over x as negative x to the negative 1. What's the derivative of negative x to the negative 1? It'll be x to the negative 2, right? Yeah. Everybody's okay with that? The negatives canceled, the negative 1 canceled the negative sign. And you could stop here. This would be fine. Or you could write it as like, you know, you could do something like this and without negative exponents. That'd be okay. Either one. Feel good? Okay. Other questions from homeworks? Again, any 3-5 or prior, anything is fine. Lucas. 44, 3.5. So the scariest problem starts, show that, right? It says show that, or show by implicit in differentiation that the tangent line to the ellipse, yada, 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 at the point, yada, 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 is the following. Oh, I took too many things. We're not doing this. All right, so let's start with the implicit differentiation. So I'll do the derivative of each side. Remember here that the x and the y are only variables. The a and the b's are constants, right? So if I do the derivative of x squared over a squared, that's just going to be the derivative of x squared over a squared. And the derivative of y squared is going to be 2y, and then I have over b squared. But because I'm differentiating a y with respect to x, it also creates a dy dx, and the derivative of 1 is just 0. So if I want to get the dy dx by itself, I will subtract the 2x over a squared from both sides. Oops. And then I'll multiply by the reciprocal. To get the dy dx by itself. So far, so good. So now I need to write the equation for a tangent line at x naught, y naught. So I know the slope for that tangent line is just the slope at that point. So I'm just going to plug in x naught and y naught. So far, so good. And then my equation for the line is y minus y naught times the slope times x naught minus, or I'm sorry, x minus x naught. Now I want to go back and look at what I have to get that to look like. Okay. All right. So let's see. Well, let's distribute this guy through, I suppose. It's just now going to get kind of messy. So far, so good. And now let's see here. I'm going to take a look here and notice that the only thing in my denominators are a squareds and b squareds. So what I'm going to do is I'm going to multiply both sides by a squared. That'll cancel out the a squareds in my denominator. And as long as I'm at it, if I look at this stuff in here, this is all a common denominator and has a greatest common factor of b squared. Let me take a quick peek here. You know what I might rather... Well, let's just keep going. You know what I think I do want to do? I think I do want to do this. Let's get rid of all the fractions here altogether. Let's try it. Okay. So what I'm going to do next is I'm going to add this b squared x naught x over and then add this a squared y naught over. So far, so good. So now I'm going to divide both sides by a squared b squared. In doing that, I'm going to have y naught over b squared plus x naught over a squared equals y naught over b squared plus x naught over a squared. So this side is all good. That's what I wanted. If I look at this side and I go back to the very beginning, that is right here. That side is 1. And we're done. The algebra got gross there, but is that okay, Lucas? Addie?
Where did can you scroll up just a tiny bit?
Mm-hmm.
Yeah. Where did the y squared, the y naught squared, you moved it to the other side? Why did it just become y?
Oh, I don't know. Let's see. Oh, it's because I also forgot to, when I distribute this over, to make that x naught or x naught squared, right? When I did that guy. So let's carry that through. But you're right, I did drop that. There we go. Thank you. I did drop it. And I made another mistake on top of it. But there we go. Good eye. Who's next? Again, would I ask you to do something like this on a test? No, but probably your college calculus professor will ask you to do stuff like this. Don't be scared. These are the best kinds of problems when they say show that this is this, because you know what the answer is. It's just about connecting the start to the end, right? And hopefully getting to here would have been okay, right? From there, it's just some nasty algebra. But you know where it has to go. As long as you're doing real algebra stuff and not making stuff up, and not make any silly mistakes like I did when I distributed and forgot to square the x naught squared, should be fine. Who's next? Michael, K.
Look at number 29,
3, 4, 29. Okay, so I have f of t equals t times sine 2t. When I look at this, I see a chain rule, and then inside of that chain rule, I see a product rule. Everybody see that? My chain rule is I have e to the x as my outer, and then t times sine 2t as my inner. And then when I do the derivative of the inner, t times sine 2t requires a product rule. So we'll start by doing the derivative of the outside. Well, the derivative of e to the x is just e to the x. So nothing really happens there. So far, so good. To do the derivative of t sine 2t, that's going to be a product rule. So far, so good. When I do the derivative of sine 2t, what do you notice there? That's another chain rule, yeah. So the outside function is sine x and the inside function is 2t. So the derivative of sine is cosine. And then the derivative of 2t, it will just be 2. We'll write that in a second, though. And the derivative of t was 1. So I should probably have a bracket here. Okay. So at the end of the day, we have, let's do it as 2t cosine 2t plus sine 2t all times e to the t sine 2t. Maybe is the best way of writing that. Does that feel okay, Michael?
Yep.
That was a lot going on there, right? We had two chains and a product in there. Woo! It's a nasty boy. Who's next? Michael K. again.
Can I do 33?
Same section, 33. Sure thing. Okay. So I have 2 to the sine pi x. So when I look at this, I see two chain rules, right? My inner or my outermost function is 2 to the x, and then the inner function of that is sine pi x. But that's also a composition. The outer function on that is sine x and the inner is pi x. So we'll start by doing the derivative of the outside, which is, again, using that same rule from Addie's question that we started with, is 2 to the x natural log 2. And the derivative of sine pi x is derivative of the outside, so cosine times the derivative of the inside, pi x, and that's just x. So if I copy this all down, we have 2 sine pi x times cosine pi x times x. Or sorry, derivative is pi. Come on, Mr. Gulick. That's what we get. Does that feel okay? What do you guys think? What's next? Addie,
You do like 75.
same section,
Yeah.
3, 4.
It's kind of long. Sorry.
Well, let's see how bad it is. Okay, so it says show that the function yada 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 satisfies the differential equation y double prime minus 4y plus 13y equals 0. Okay, so my plan here is going to be to find the first derivative and then plug it in for y prime. The second derivative, plug that in for y double prime, and then we'll just plug regular old y into that. And hopefully that'll all simplify out for us. So we'll start. To do that, we'll do a product rule. So we'll have e to the 2x times the derivative of a cosine 3x plus b sine 3x plus a cosine 3x plus b sine 3x times the derivative of e to the x. So if I do that, we're going to have the derivative of cosine is sine. So I have sine 3x, and then the derivative of 3x is 3. Is everybody okay with me like shortening up some of the work that I'm showing, because this problem is going to get real overwhelming real quick? Okay. Derivative of sine 3x is cosine 3x times 3. And then I have a cosine 3x plus sine, b sine 3x e to the x, e to the 2x times 2. So there's my first derivative. Let's change colors here, and we'll do a second derivative. So I'm going to have e to the 2x times the derivative of negative 3a sine 3x plus 3b cosine 3x plus, I'm going to push this 2 inside. Oh, sorry, I still have the other, sorry, no. And then I have negative 3a sine 3x plus 3b cosine 3x, derivative e to the 2x, and then plus, I have my second piece. So I have 2e to the 2x times the derivative of a cosine 3x plus b sine 3x plus a cosine 3x plus b sine 3x times the derivative of e to the 2x. Just do that. Okay. Yuck-er-rooskies, right? All right, well, let's start plugging this thing away. So I have, let's do this. We still need to, all right. So the derivative of negative 3a sine 3x is going to be negative 3a cosine 3x times 3 plus 3 negative sine 3b negative sine 3x times 3 plus negative 3a sine 3x plus 3b cosine 3x times e to the 2x times 2 plus 2 e to the 2x, and then we have a negative sine 3x times 3 plus b cosine 3x times 3 plus that's gone there, and we'll do 2 a cosine 3x plus b sine 3x e to the 2x times 2. All right. So let's see here. We're going to have everything has an e to the 2x stuck to it, right? So I'm just going to take that straight to the front. And that's going to be negative 9a cosine 3x. And I have minus 9b sine 3x. Then I'm going to distribute this 2 through to make that minus 6a sine 3x plus 6b cosine 3x. Now I'll distribute this 2 through. So that's going to be minus 6a sine 3x plus 6b cosine 3x. And then we'll distribute this 2 and this 2 through. So then we have plus 4a cosine 3x plus 4b sine 3x. And then let's see here. So we have negative 9a and then cosines. And then I have positive 4a cosine, so that's going to make negative 5. Let's see, we have a negative 9b sine. And then there's a 4b sine. I have a negative 6a sine, another negative 6a sine, so that's negative 12a sine. Is everything looking okay so far? Oh, thank you. Yes. Perfect. Thank you, Lucas. And then we have a plus 12b cosine 3x. All right, so that is our y prime. Or y double prime, excuse me. All right, and then we're going to add to that minus 4 times our y prime, which will do so I'm going to pull that same e to the x out front. So I'm just going to leave this stuff inside. Is that okay with everybody? Then I'm going to have negative 3a sine 2x. And then I'll have a plus 3b cosine 3x. And then I'll distribute this 2 through. So I have a plus 2a cosine 3 and a plus 2b sine 3x. And then what's left here? Plus 13 and the original. Again, because that has a e to the 2x stuck onto that also, I'm not gonna put it all inside that same big set of parentheses, so that's just gonna be a 3 cosine x. And then b sine 3x. All right, so let's see what we get here now. So let's distribute the negative 4 through. So that's going to be plus 12. That'll be minus 12. Be minus 8. That'll be minus 8. And we'll bring that 13 through, so that'll be 13 and then plus 13. All right, let's go like term hunting here. So negative 5a cosine so that's negative 8a more, so that's negative 13a cosine. And then positive 13a cosine, that's all 0. And then we have a negative 5b sine. And then we have a negative 8b sine, so that's negative 13b sine. And then, oops, I copied that wrong, didn't I? That's supposed to be a sine there. And then I have my positive 13b sine. Those are all gone. This is like an exercise in bookkeeping here. So I have negative 12a sine, and then a positive 12a sine. Those are all gone. I have a positive 12b cosine, a negative 12b cosine. Those are all gone. So what are we left with now? It's just e to the 2x times 0, which is 0. And we're done. Whoa! That was miserable, but doable, although it takes like a sheet of paper. Look, what was the hard part of this? It was really just the bookkeeping piece, right? Like the calculus that we had to do. Was there a bunch of chain rules in there? Yeah, but they were all just like one chain rule at a time. Were there a bunch of product rules in there? Yeah, but there's just like, as long as you were able to keep track of where you were in the problem and avoided making like a transcription error. The algebra was gross, at the end. Like, it was a huge thing to keep track of everything, but like doable, really long, really tedious, but like, doesn't that feel good when it just like everything just cancels out and it's like, oh yeah, I did it. Gives me a lot of satisfaction. You know? Addie, are you happy?
I mean, I'm glad I see it worked out. There's no way I would be able to comprehend this.
It's, again, the hardest part is just like grinding through the detail, right? Like, is that a lot to grind through? Yeah. Do you understand the process? Yeah.
Will there be anything like there won't be anything like this on the test?
I mean, it would be the one question would be the only thing I could put on the test. It would take you 80 minutes to do this. What am I, crazy? I'm not interested in having you do more than one question. I mean, maybe 1.5, right? Maybe that's an hour and then 20 minutes for something else. No, I wouldn't ask you to do this again. Like, that was, I mean, it took me, I think, 15 minutes to grind through it, like showing my work. You know, like, it's usually a 4-to-1 conversion. That's like an hour problem for you. You know, like, yuck. It's not worth test time to do something like that. Although I think, like, really beneficial to grind through and make it work. Like, boy, you're good at hanging on to, like, you know, like your symbol pushing, if you're able to get that to work, which is the reason I assign it, you know. All right. Let's stop here with questions, yeah? What I've handed you guys is a packet. I think there's 30 multiple choice questions on there. All these problems are basically just like product quotient, chain rule, implicit differentiation, scattered through there. They're all multiple choice, so you're going to have to simplify your answer well enough to figure out which one it is. This is something that I'd like to collect from you. So, like, do it and collect it. I'd like to get you, like, mark some stuff right or wrong, give you some feedback. I'm not going to score it right and wrong, but I'd like to mark it. Since it's multiple choice, it'll be relatively easy for me to mark a bunch of them and get you some feedback. As far as things go, I think that this section 3.5 is the hardest thing we do for test 3. So I'd like to settle in and have some time to practice here on some of these skills, as like all the product quotient chain rule stuff is all stacked onto the implicit differentiation piece. So if we're kind of shaky in any one of those, like, the implicit stuff is hard. So we'll do that for the rest of today. Anything you don't finish, you can continue to work on until next class, no big deal. For the asynchronous day, what do we have left? I'm going to give you guys a short video lesson for 310. I'm going to go a little bit out of order, but 310 is very standalone. Okay, basically, the whole idea of 310 is going to be writing the equation for tangent line and then using it to make an approximation. So if you can take a derivative and write the equation for a tangent line and then plug a value back in, you're going to be all set. It's not a difficult section. Although the book, if you look at the book's explanation, it seems really difficult. Don't look at the book for this one. A lot of times the book does a wonderful job on stuff. Section 310 book makes it like a miserable, confusing mess. I'll show you exactly what you need to be able to do, and it's really easy. Again, it's stuff we've done. It just has a new name now. Everybody cool? Okay. I'm going to stop talking and let you guys get cranking on your packet.